So anyway, I do have some interesting, I did want to show some interesting things, like how did people figure out what the energy of a photon was. They did it with semiconductors, so that's kind of neat. There's also a little interesting bit that this experiment done 20 years, it's been a while, 20 years ago at MIT, where they proved that matter has wave-like properties. I can show you that. And then I promised you I'm going to show you how I engineer Maxwell-Boltzmann on the test. I think that'll really help stick how you deal with this stuff, even though I'm not asking you to do the same thing. Before I do any of that, do any of you have any questions or want to do a problem? Because I don't mind. And again, it would help if you folks looked at the homework before today, but I understand if you don't. No questions? Okay, so tell you what. The engineering, the Maxwell-Boltzmann only takes about 20 minutes, so let me just show you one or two things that are kind of neat about how people figured out what the energy of a photon is, which is the photoelectric effect. I'm looking at my notes because I don't know how to spell photoelectric, by the way. Okay, the photoelectric effect. Okay, so what happened was, I'm sure you might have heard this before, so it's around 1900, and now people have electricity, and one of the first things that physical chemists did was they started building vacuum pumps, because everything you measure is way cleaner if you don't have gases getting in the way of things, especially electrons. So one of the things that you can do is take a semiconductor, let's take silicon, and you shine light on it. And as is the usual convention in science to say Planck's constant h times the frequency is, when you write that, not only you're trying to signify that this photon has a certain energy, you're trying to signify this is a photon, by the way. Okay, so what happened was they would shine light on a silicon, and because they have this in a vacuum, which by the way, this type of spectroscopy is still done to this day. This is unfortunately, I had my materials that I synthesized in my lab characterized via this spectroscopy just a few days ago to the tune of several $100s. So this is a photoelectron spectroscopy. It's still one of the most modern things that we do. And so at the time, what happened was they had like a piece of silicon and they have it in a vacuum, and they shine low energy light, like about 1,000 nanometers, which you know now is infrared, and nothing happens. So like what? Why are you doing that? Okay, now low energy equals long wavelength. Okay, now go to short wavelength. And the reason that this is special, and the reason that people only figured this out when they had vacuum chambers, is because, here, let me just finish drawing this, and I'll make sure that the energy of the photon is greater by making it wavier. What happens is, once you get energy of the light being greater by using shorter wavelengths than 1,000 nanometers in the visible, when it gets in the visible, red is in the visible, right? Infrared is out the visible. So when you use infrared, you don't see anything, but when you use red to higher energy, electrons start coming out. And this was, again, the photoelectric effect. And they only found out that this was happening because they had vacuum chambers. Because if you do this just out here, the electron goes probably not, what, how maybe 70 nanometers? Why am I saying 70 nanometers?
The radius of the gas.
Right, it'll hit a gas. It'll hit a gas. If an electron hits a gas molecule, it's gone. It'll stick to the gas molecule, right? And you know that it won't have to travel too far before it hits a gas molecule. So you have to do this in a vacuum chamber. So only when we had electricity, so that we could reliably work with equipment, did we discover this effect. Did I say selenium? Silicon. Okay. Now the thing that flummoxed them, though, was that they could make infrared light really intense, and you do that with a glow bar. It's a light bulb with a really thick filament, that's all it is. They could make this incredibly intense and no electrons came off. This is kind of counterintuitive because you can put your hand on this and you'll get burned pretty badly. So this is like a lot of energy. A lot of a lot of infrared photons is a lot of energy, and it hurts. Yet the silicon doesn't respond. Then you lightly add some visible light, just a light bulb, which doesn't hurt at all. I'm not being burned to death. Yet the electrons start getting shed off the silicon like mad. And this was kind of confusing. But the answer is that the energy of light is not proportional to its intensity, but its wavelength. And remember, this is like totally different. Remember that they have just figured out things like the equipartition theorem for gases, that your energy is 1/2 mv squared and all that stuff. They figured all that out, but electrons are behaving completely differently. Their wavelength is what dictates that. So that's unusual. And now the way that they figured out what Planck's constant was and how to figure out the energy of a photon is this. This is an energy diagram. And so what you do is you take silicon and you ground it. So what I'm doing, I'm drawing energy on the y-axis, and the x-axis there really isn't an x-axis. I'm like drawing an object basically. So you take silicon and it's grounded, literally, and I don't mean like it's grounded in reality. It's got a wire bonded to it and it's stuck in the ground. Okay, and so then what happens is that it has a band gap. It has a band gap, which is about the energy of a 1,000 nanometer photon, an infrared photon. And so what happens is if you shine lower energy photons, 1,000 nanometer photons, you just don't have anything happening. 1,000 nanometers is close to the band gap, but just not quite, Now, do 700 nanometers, which is definitely red. That's pretty much at the limit of what you can see. There you go. It's more energy. So this is an IR photon, and this is an actual red photon. 1,000 nanometers versus say 720. Again, that's the limit of your eyes ability to see. Then you get an electron kicked out. And electrons, now this is why this was very fortuitous that they figured this out. Electrons have no internal structure. They're not rotating, they're not vibrating. So that energy is pure kinetic energy. And it turns out that is just basically 1/2 mv squared. Now you know the mass of the electron, and it ends up being the energy of the photon minus the band gap of say, if they did silicon, if the silicon works pretty well, then that's how they know that. So what they're able to do is, the band gap of silicon is a constant, so what they can do is map out the kinetic energy of a photon versus the wavelength of light, and guess what the slope is? It's Planck's constant. That's how you figure out Planck's constant. Another thing is that's kind of, that you get out of this is that light is behaving as though it has momentum, because electrons, if you hit an electron, you convey energy and momentum. So remember that we have all kinds of rules that have to work simultaneously. We've got the speed of light is constant, we have energy is constant, we have momentum is constant. Angular momentum especially, that's a real Bisnocker. Whenever you have a thing happen in science and you're analyzing it, you have to make sure that you keep those constant. Can't violate the speed of light, can't have total energy increase or decrease, and you got to make sure angular momentum is all solved. And so anyway, so this is an aspect, you're kind of seeing that basically show up here. And now when it comes to preserving kinetic energy, you do that by energy, but you also have to have momentum. The electron also has to have momentum too, because it has mass. But that also means that the photon has to have momentum. You can't convey momentum to the electron without the thing that's hitting it having momentum too. So on your homework, Einstein figured a lot of this out. He figured out that, and I'm writing this off the top of my head, what is it, is this right? I'm doing this off the top of my head, but I've been doing this for a while. Yeah, this is right?
Yeah.
E squared, C squared? Right, now, what's that?
E squared.
E squared, right, E squared, right. So, for a photon, the mass is 0, that's true. So you end up with the energy being Tc, and therefore momentum of light is what's my H over, well, I mean, yeah, let me put HC over lambda, that's better. And then P is H over lambda. So again, just to summarize, and you did that on your homework, I just want to remind you that the photoelectric effect gives you not only Planck's constant, gets you to understand that the energy of a photon is proportional to its wavelength, but again, if you're going to hit an electron, it's got to conserve momentum and energy. Now, we just did energy, that's kind of easy, but the people back then were like, wait a minute, okay, but then the photon also had to have momentum too. It had to have both energy, not hard, and momentum. Whoa, that doesn't make sense. Light should not have momentum because it has no mass, but then they looked at Einstein's equation and said, no, wait a minute, light does have momentum. So when light hits the electron, it can give its energy and its momentum, and it has to because electrons have momentum and energy. So anyway, that solves that conundrum. So that was kind of cool. The last that I wanted to mention, talk about waves before we get, remember I was saying that quantum mechanics is better described as wave mechanics than I prefer the term wave mechanics than quantum mechanics because you always run into waves when you do these problems, but you don't always find that energy is quantized, and we're going over that shortly as we speak out loud. When you run into this concept in heat capacity. And again, this is one of the things, I think I spelled that right. This is one of the things that with the photoelectric effect, relativity, light has momentum, yada, 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 people start figuring out that you need to start thinking of matter in terms of waves. And that, light as a wave is not hard, and you learned that in middle school. Maybe, you're kind of nerdy, right? So you remember, you probably played with prisms when you were little, right? So you knew that light was a wave. So I knew I was playing with those in middle school when I'd get a prism when I visited the planetarium and whatnot. And heat capacity is a good segue into knowing that matter has wave-like properties too. And so what people figured out was they put a piece of silicon in a calorimeter and they would heat it up. And you know that you can, as you measure the temperature rise, and you know how much heat is added because you're adding heat. And again, this is around 1900 when people had electricity, they had vacuum pumps. They also, what generated the Nobel Prize was someone figured out how to make an ultra refrigerator. This guy named Joe. It's an unfortunate name, it's French. But so he figured out how to make sub-Kelvin freezers. And so they would freeze things and then warm them back up. And it's easy to warm things back up because they use like a light bulb. So what that allowed people to do was to measure the heat capacity of solids, and they would rise, and of course they'd level out. Now you know from last class that then there's a heat capacity jump when it liquefies, and then there's another heat capacity difference when it turns to a gas, but we're just looking at the solid. And what they found was that there is a T, it rises as T to the 3. Okay, so people were trying to figure that out, and Einstein was like, when he was quite young, and he actually messes this up, by the way. Einstein actually did not believe in quantum mechanics, so he made a decent number of mistakes, and that's kind of a whopper, by the way. This is another one of his mistakes. What he said, now, he got the ball rolling in a great way, but he flubs it at the end. Now, here's what he got rolling. He said you have to think of this solid as having atoms that are vibrating. Right, so here's a solid, there's the atoms, and they're vibrating. And so what he does is he makes this analysis, and he says that they vibrate at a wavelength, and they can vibrate with any energy. Now, heat capacity is taking thermal energy and causing it to vibrate more. That was the idea. Now, you probably know this to be true. There's actually a slight mistake. Anyway, again, solids are composed of atoms. Check there. Atoms vibrate. Now, you've heard that before. Phonons, right? Einstein's got that right. But he says they vibrate at a single frequency, and as the thermal energy comes in, it just vibrates more. Actually, kind of wrong. Kind of wrong. And so his data, his fit goes like this. Goes like that. And he's like, at first, supposedly everyone was like, well, look at that, he got the right, he almost has it right. And then, but people were like, yeah, but almost. And this is another neat thing about facts in physical science, almost doesn't cut it. So people thought at first, they're like, well, here's the data. They're like, oh, yeah, look at that, it's fine, Einstein has it right, Einstein's describing things correctly. You see, if this was correct, in terms of error bars, then there really is nothing to worry about. But as this guy Joke made better and better refrigerators and instrumentation became, just worked better, here's Einstein's fit, and here's the data, and no, it doesn't work. It does not work. It does not fit. I mean, yes, it was very, very close, but sorry, you don't have it right, because this has got to be perfect. Because of that, I mean, it's just really pissed. Can you imagine how pissed off people were? It's like, oh, come on. Just get the error bars a little bigger. This has got to be right. The measurement's wrong. No, the measurement's not wrong. You were sure about it. Okay, here's the answer, by the way. And I thought this is like one of the coolest things I know. Okay, so now Einstein said that there's one wavelength. And deBroglie comes along and says, no, you made a mistake. There's multiple wavelengths. There's low energy wavelengths. Now let me give you a low energy. So I'm drawing atoms in a lattice. I'm drawing obviously a very simple lattice. Here is the atoms moving like a wave. Hear that? It's a wave. Now this chunk of silicon is L long. What's the wave of that phonon? What's the wavelength? 2L. 2L. It's 2L, right? So that's a low energy phonon. Now, what you could also do is something like this. Right? So the wavelength is L. Okay, right. So deBroglie figures out that atoms move like waves and they can have different wavelengths. Now, let's do this. Now, this is where he actually gets it to fit perfectly. He gets T to the 3. The point here is that this is your maximum wavelength. I know that the scale is screwed up. Solids are not 4 atoms wide, okay? There is an upper wavelength because you can't get atoms to move. I mean, so let me put it this way. Is this legit? Is that a legit wavelength? No, it's not legit. No, it's not, basically it's saying that this motion, moving at twice the frequency, still moves like this. What? Huh? Oh, no. No, those atoms, if they move at twice the frequency, would still appear to move the same way. No. So you're right. If you're thinking like, what am I doing? I'm babbling like an idiot. Yes, I am babbling like an idiot. That is not a legitimate wavelength. There's an upper limit to the wavelength, which is basically the distance between atoms. So when deBroglie says, no, there's not one wavelength, but a bunch of them, and there's an upper limit to the wavelength, and then he repeats the analysis, the data in the fit were what have I done? That's Einstein. That's Einstein's fit. Here's deBroglie's. Peter deBroglie's fit was absolutely perfect. But the point of this was, he's starting to interject that matter has wave-like properties too. That was the idea. And then you had deBroglie. deBroglie comes along, and I wish I understood this a little bit better. deBroglie's thesis is supposedly very, very long. But what he did was he looked at Einstein's revelation that photons have momentum. Now remember, this is nuts. Photons have no mass. How can they have momentum? Well, then they wouldn't be able to knock electrons out of semiconductors, and they do. Einstein's equation predicts it. That's Einstein. deBroglie looks at that. Let me write that down. Right, deBroglie looks at this, and he makes this rearrangement. Now, again, I'm sure that it's more complicated than that, and you're doing this on your homework. He says that matter has a wavelength. Kind of like I was just talking about heat capacity. Matter has a wavelength. So, momentum of matter. Now, that's understandable. It has mass, has velocity. Not hard at all. Divided by Planck's constant, it has an associated wavelength. And this was proven to be true in 1999 at MIT. Did I say 1990? 1999. 1999 at MIT, they were able to build a diffraction grating and shoot buckyballs at it, C60, and they diffracted against each other. Matter diffracted against itself inside a diffraction grating. Now, you're used to light diffracting in a diffraction grating. They got matter to diffract in a diffraction grating by shooting C60 at a, the real clever thing was they built a diffraction grating for matter by etching silicon. So what happened was they managed to etch silicon so that it had holes in it. And I'm not drawing this right, and I can't do it. I'm not even trying to flub it. So they got a piece of silicon and drew slits into it with an electron beam, shot C60 at it, and so there was like slits, and it diffracted. So there you go, that proved it. Any questions? So tell you what, that's what I've got about the stuff that happened around 1900 that then led Heisenberg in around 1930s to write a paper where he wrote about quantum mechanics. And unfortunately, Heisenberg used a mathematical representation that confused the living hell out of everyone. No one understood what he was saying because he actually represented what would be known as the Schrödinger equation in the form of a matrix, and that confused everybody. Schrödinger independently came up with quantum mechanics. He was skiing, and it suddenly hit him, waves and matter, and he hit a tree. But he lived, and then he would later come out and write the Schrödinger equation. I might as well just show you. This is what it is. He wrote this out. Here, I'll write the whole thing. This is the Schrödinger equation. By the way, obviously I'm doing one dimension just because it'll blow your head off. Okay, that's what he figured out. This was easier to look at, swear to God. It was just easier to look at than what Heisenberg wrote. So Schrödinger got credited for discovering quantum mechanics, but actually Heisenberg did it before him. Again, this is just easier to look at, right? So people understood it faster, but Heisenberg really got it first. So anyway, this is what we're going to start on Monday. So let me just write that out. All right, any questions? We're all okay. So let me show you what we're really here for, which is how do I design questions on your exam? And I think you'll find this kind of fun, because I hope that you'll really get how the Maxwell-Boltzmann equations work. Okay, Maxwell-Boltzmann equations on exams work. Remember that if I ask you, what's the average number of pigs in a blanket, and you set this up, you find an identity, and you get the number 1, have you done it right? What do you think? Have you done it right? So again, What's the average number of pigs in a blanket? Oh, I know how to do that. I'm going to integrate this Maxwell-Boltzmann equation. I'm going to find an identity. I found one, and the number is 1. The answer is 1. What do you think? Danger zone or not? It could be, but I'm telling you you're in the danger zone. Maxwell-Boltzmann equations are normalized, right? And then the average must be what I want. Okay, again, you're on the exam, and I write a Maxwell-Boltzmann distribution question. I'm asking for the average pigs in a blanket. You have set it up to the best of your ability, you found an identity, and you get the number 1. You might be doing this. You might be proving that it's normalized, which it will be normalized. I made sure of it by the procedure I'm about to show you. But did you calculate the average? It could be true that the average is 1. Maybe you did it right. But you're in a danger zone because you could have just shown it was normalized and you didn't calculate the average at all, right? That's one of the things to look out for. It's the most common mistake. Now let me show you how I set this up to make it work. Now, I'm not trying to screw you over. I'm not trying to make you find 1.0 that is normalized and you actually didn't calculate the average. It's just that I've got to make sure that all of this makes sense. I don't want to throw nonsense questions at you. Okay, so let's do the first one. Now, when it comes to writing down a Maxwell-Boltzmann question, I have to come up with something. And again, I'll do something silly because it's just not that important that you can regurgitate average velocity. It's just not important, right? Not in the long term. But if you know how to correctly calculate averages of things that you might actually run into, that would be infinitely more useful to you in the purpose of an education. So I'm going to write an equation. I'm going to come up with a distribution. Now, of course, I'm going to have an e to the minus. I'm going to do pigs in a blanket. So I'll start with e to the minus pig squared. Okay, now I am creating a bell-shaped distribution. Bell-shaped distributions are a little too boring. The average is at the center, most probable is the center, and that's just not interesting. So tell you what, and to make it more Maxwell-Boltzmann-like, pig times the bell, and that gives it a slant. So now I've got a skewed distribution. Okay, so again, when I write these, the first thing I have to do is I have to come up with a distribution. I usually like to do a slanted distribution because it's more interesting. It also is more similar to the Maxwell-Boltzmann without actually being the Maxwell-Boltzmann. Okay, now, average pigs in a blanket. Now, where's blankets? Here's a hint. I'm missing something. I'm not done designing this question. Pigs. Let's say pig is a unit. It's a joule. Right. So what have I done wrong? What about right here?
It's not unitless.
It's not what?
Unitless.
It's not unitless, right. So what I'll do is I have to divide it by something. B for blanket. I'll just call it B. Right. Okay, I've got to have the e to the something normal. I've got to have no units. E to the blah cannot have units. The arguments of an exponential cannot have units. So now I've done two things. I've got my pigs and I've got my blanket, so I wanted that. I've also got e to the blah, the argument of the exponential is now unitless, and that has to be true too. I also know that now that whatever the unit of a pig is, a blanket has the same unit. And again, this is all, I know this all sounds silly, but it's fanciful, but whatever. Okay, now the next thing is, now let me get this ready for integration. Okay, so now I've got pig. Now I know I'm going to integrate it. Now the question is, am I going to integrate it correctly? So I've got minus pig squared over b squared. And again, I'm going to be integrating with respect to pigs. This is the whole Maxwell-Boltzmann distribution for pigs in a blanket. I actually still have a unit problem. Remember, the Maxwell-Boltzmann has to have no units. What are the units of this thing?
Pig squared.
Pig squared. Pig squared. The exponential is taken care of. No units. Pig, partial pig. Both have units. So, again, what I'm doing is I'm just showing you how I've come up with the form of the Maxwell-Boltzmann. I have to follow design principles before I even begin. So the argument is the initial cannot have units, nor can the entire thing have units, and that's when I have a partial as well. I can't forget that. So don't try to memorize that. I'm just showing you. Remember, you're not doing any of this. I'm showing you how I designed the question on the exam. I think this is useful to you. Okay, now that I have this, now I can actually start the hard part. What I've got to do is I've got to normalize it. Okay, now for thing number one, sorry, step 3, what am I doing? Well, but this is related to point 1. It has to be normalized. Okay, so the normalization, I'm going to call it n, because I'm not quite sure what else to do here. N over b squared, pig, e minus pig squared over blankets squared, e pig. This has got to integrate to 1. Now I will also make sure that you know what the proper limits are, because again I'm coming up with something fanciful. I will probably just explicitly tell you what the limits are. If you get that wrong, then you're hosed. So I'm not going to let that happen. I know it's kind of silly what I'm doing, so I'm not going to simultaneously screw you over on my silliness by not telling you how to solve it. Okay, now you've seen this. Maybe somehow this is on an exam, or I'm designing this, and so I have to look this up. I see this, and I see that the answer is 1/2, 1 over 2a. Okay. So, okay, so now what do I get from that? I get, oh, wait a minute. You know what, I'm missing something. I've got it normalized, but I can tell you that I forgot something here. I've got the units out, but I have no ability to control. I have no ability to control the average value, so I need a constant here. I need a constant there, or I can't control the average value. Sorry, I just, I realized I made a mistake when I wrote that A. So anyway, right, Fridays are bad. I'm just nutting on these days. Okay, so yeah, so I've got okay. So now what do I do with this? Now I know it's kind of equal 1. I've got n over b squared. Those are some constants. The b squared, it's again there because it's got to be, the unit's got to work. The n is the normalization. That's what I'm actually looking for. Okay, then I've got the result of the integral is 1/2, and a, let's look at this, a is c over b squared. So that means 2 times c, and then the b squared is on the top. Okay, so therefore, n is equal to 2c. See that? The b's cancel. Look at that. B's cancel, so n is 2c. All right, so now again, sorry that I kind of fluffed a little bit when I forgot about the c. So I designed this such that I don't have units. So that's how I get the b squared here, the b squared here. Now I have to have the c again. This is the part I forgot because that's how I manipulate the average. Now the first thing to do is make sure it normalizes properly. To do that, I get a normalization constant, and I figure out that n is 2c. Notice that I haven't actually figured it out yet, because what I've got is an equation with 2 unknowns. I've got an equation with unknowns of n and c. I've used one equation, but now I need another one. Now here's what I do. Here's step 4. I have decided that I want the average value of pigs. So I take pig times the Maxwell-Boltzmann distribution. And I want this to be 10 blankets. So again, I'm designing the thing. I've got to have it normalized. I haven't quite gotten it yet because I have one equation with two unknowns. To solve for n, I've got to make some other stipulation, which is that I want the average value to be something that I just come up with, right? Because these are all fanciful. I just decided to make it 10. I try to make them all, always the numbers are like, not weird or like, you know, it's not like pi blankets because that's strange. 10 blankets, I don't know, just I like that. 10 sounds fine. Okay, now how do I do that? Okay, let's see here. Now, let's write the normalization. That's 2c, that's normalization, b squared.
10 bigs.
What's that?
10 bigs.
10
In your analogy.
a blanket is, remember this pig's in a blanket, so I can make it a blanket. I can make it a pig or a blanket. Pig is a blanket. Now remember how average velocity. Let's think back to Maxwell-Boltzmann. Let's go back home. Let's make it easy. Average velocity is 8 kbt over pi m, square root of 8 kbt over pi m, right? Velocity is basically kbt in that. Pig is a blanket. Now how can a pig be equal to a pig? Right now, I didn't have velocity is equal to velocity. I didn't have velocity is equal to 3 velocity over 8 pi velocity equal to, anyway, so you see where I'm going with this? When I had an average value of something, it's in terms of something else that I have. Like I have velocity in terms of kb, t, and m. Right? Because that's just sensible. Right? So again, average velocity. Sorry, I'm getting myself a little bit confused because I'm just kind of blabbering a little bit. Okay. Now this is the Maxwell-Boltzmann thing, and hopefully you're kind of okay with this, right? I don't have velocity in terms of velocity because that doesn't make sense. I mean, it does. It's perfectly correct. So what you're doing that. You're making the pigs a pig. Sure it is, but that's not useful. Here I've got velocity in terms of kbt over m, just like I have pig in terms of a blanket. Right? If I'm going to put velocity in terms of velocity, it's just velocity equals velocity. That doesn't do anything. I'm putting pig in terms of something else. That's the purpose of this. And remember, pigs and blankets have the same units. Question?
Yeah, are we assuming that pigs and blankets are continuous because we're integrating?
Well, now I would give you that information, and yes. Right, so I don't leave you hanging on. Now, I know that this is all weird, but again, I don't really care that you remember that the average velocity of O2 is 500 meters per second. Those things you're going to just forget as soon as you walk out the door. What I want you to do is get kind of a big picture on how to do this correctly. On whatever you run into. So I'm intentionally picking something really weird, but I want to see that you can still hack it. Now of course, I will still make sure that I'm going to tell you integrate it and here's the limit. So I'm not going to leave you like in La La Land. Real quick though, because I got to finish this. So what you end up with is this guy here. Essentially something that looks like pig squared. Remember, the extra pig comes from okay. Now, are you solving this right? Well, what you're looking for in the handout is this formula, which is square root of pi over 4, 1 over a to the 3 halves. Okay, again, so this is like when I'm designing it. So now what I get is I've decided that the average number of pigs is 10 blankets. I've decided that. What it's equal to is 2c over b squared, square root of pi over 4. And then if I plug in what a to the 3 halves is, that's c to the 3 halves over b cubed. And what you end up with is C is pi over 400, and of course N is 2 times that, 2 pi over 400. Okay, and therefore, the Maxwell-Boltzmann distribution I give you is 2 pi over 400 b squared. Sorry, I don't necessarily integrate it. This is the Maxwell-Boltzmann. Pig e to the minus, where am I at? Minus pi pig squared over 400 b squared. Okay. Now again, what I've done is I decided on the form of the Maxwell-Boltzmann distribution, but it needs to be normalized. So I wrote an n here, and I had to figure out what n was. I had to make the average 10, so I had to have a little c there. This procedure allows me to figure out that n is 2 pi over 400, and c is pi over 400 right here. So with that information, I can then write out the whole Maxwell-Boltzmann, and for the hell of it, just for the hell of it, given the information I've already given you, double check that if you integrate this from 0 to infinity, what do you get? What do you get? You would get what? 1. That's right. Integrate this, I swear it comes out to 1. Integrate this, what do you get? 10 what? 10 b's. You'll get 10 b's. The unit of b, a b will survive the identity when you do all the processing. So anyway, sorry I got a little flummoxy there, but that's how I do this. I hope that's going to help you on these things.